Hello dear students. So in the previous classes we have been discussing about the oscillators. Now we'll be proceeding with the oscillators. So in the oscillators we have seen the definition, the basic principle, the types. Where in the types we have seen that there are tuned oscillators called as LC oscillators and also RC oscillators and crystal oscillators. Okay, so before moving into the types of oscillators, we'll be seeing what is a tank circuit. Tank circuit. Okay. So what is a tank circuit? Tank circuit is a circuit that can generate or produce a voltage of desired frequency. Okay, so definition of the tank circuit is basically matching with that of the definition of the oscillator. So definition is nothing but the definition for oscillator. But how the tank circuit is different is the tank circuit can only use inductor and capacitor. Okay, whereas oscillators can be constructed otherwise formed with any other or different components also. So this tank circuit. So now basic operation of the tank circuit. Basically, a tank circuit comprises of a capacitor and an inductor. L and C. This is a switch. Okay, which can take the position as 1 and position as 2. When it is at the position of 1, it will charge the capacitor. Okay. Here, when the voltage supply is connected to the capacitor, the switch is here. Okay, this is a switch. When it is connected to the position 1 here, this is a switch. Control is with the capacitor point. When it is connected to voltage source, it will be charging up to the value of V, that is maximum charge. When it is thrown to the switch 2, it will start discharging through the inductor. So simple concept of this tank circuit. So example of the tank circuit is shown here, that is having one capacitor and one inductor. One capacitor and inductor is there. Okay, so this is tank circuit. Now the operation of this tank circuit, what all happens? Initially, when the switch is thrown at the position 1, switch at position 1, switch at position 1. What happens? The capacitor charges. The capacitor charges. Switch at position 1, the capacitor charges. Okay. To the maximum value, to its maximum value. Right. Next, once capacitor is fully charged. Once capacitor is fully charged. Okay. So considering this circuit, initially the switch is at position 1 and it starts up to the maximum value, right? And once capacitor is fully charged, now charging process is complete. The capacitor is completely charged. Okay. What happens? Switch is connected to position B. Connected to position 2. Okay. Switch is connected to position 2. Next, what happens now? The capacitor starts to discharge through inductor L. Through inductor L. Okay. Switch at position 1. When initially it is at 1, the capacitor charges. When the capacitor is charged to its maximum value, once capacitor is fully charged, the switch is connected to position 2. Now the switch will be connected to what? Position 2. When the switch is connected to position 2, the position of the switch changes. Now what is happening? The fully charged capacitor. The capacitor that is fully charged is going to discharge. Now it will start to discharge through inductor L. Okay? Inductor L. As a result, and magnetic field is developed across the inductor. Developed around the inductor. Okay. So what happens here? Switch at position 1. When the switch is at position 1, capacitor charges to the maximum value. Once it is fully charged, switch is connected to position 2. When the switch is connected to position 2, capacitor starts to discharge through inductor L. As a result, a magnetic field is developed around the inductor. Right? Now the inductor is having some magnetic field around it. Now what happens? The capacitor is once the magnetic field is developed around the inductor, when the capacitor is fully discharged. Okay, once the capacitor is fully discharged and the magnetic field is generated around the, otherwise developed around the inductor, what happens? The inductor The inductor magnetic field starts to collapse. Collapse. It starts to collapse. Okay. So as it collapses, what happens? The capacitor again starts charging due to back EMF of inductor. As the magnetic field developed is collapsing, otherwise is dropping, the back EMF is going to charge the capacitor again, and it charges. Capacitor is charged with negative polarity. Is now charged with negative polarity. Okay. Now it is charged with negative polarity. Again, once it is completely charged, it is going to again discharge through the inductor. Again, a magnetic field is developed across the inductor, and again the back EMF, it is going to collapse. The back EMF is going to charge the capacitor again with opposite polarity. Okay. So once the capacitor is charged, again it will be discharging. It will be charging. The charging and discharging process is going to produce the oscillations. So this charging and discharging process of the capacitor is going to produce the oscillation. So how it is? Switch is at position 1. The capacitor charges to maximum value. Once it is completely charged, once the capacitor is fully charged, switch is connected to position 2, where now it is the capacitor is connected to the inductor, right? Now the capacitor starts to discharge. Now the capacitor is going to discharge through the inductor. As a result, a magnetic field is developed around the inductor. Now the inductor is also charged and it develops a magnetic field across it. Then the capacitor is fully discharged. Now the capacitor is completely empty. Now what happens? The inductor magnetic field starts to collapse. Okay. Now it is going to collapse. The capacitor again starts charging due to the back EMF of the inductor. As it is collapsing, the voltage is the magnetic field of it is dropping. As a result, what happens? The back EMF is going to charge the capacitor again, but the capacitor is charged with opposite polarity. Okay, it will be charged with an opposite polarity, right? That's why the continuous cycle, this process, continuous process of charging, discharging, charging, discharging is going to produce the oscillations. Okay, but this particular circuit produces damped oscillations. Why damped oscillations? Because it is not satisfying the Barkhusen's criterion. That means there has to be one amplifier and also a feedback path. Okay, there has to be a positive feedback and a beta. That means loop gain has to be equal to 1. These two conditions, if satisfied along with this tank circuit, it will be acting like a undamped oscillator. Clear? Along with this tank circuit, if it is going to satisfy the Barkhusen's criterion, then it is going to act like a oscillator. Here, so this is about the tank circuit. This circuit having a capacitor and an inductor, where capacitor charges and it discharges through the inductor. Inductor develops a magnetic field across it, around it, and then it is going to collapse, charging the capacitor in opposite polarity, and this process can be used to generate the oscillations, otherwise to result into the oscillations. But what is the drawback is it is going to be damped. If the value is going to reduce as the process is continuous charging and discharging, charging and discharging. At some point, it is going to reduce the value. Otherwise, the signal generated is going to be reduced. Okay. And now, why does this happen? This happens because of the inherent resistance properties of all the devices. Inductor is having a inherent resistance property. Capacitor will be having a dielectric resistance inside, and the wiring, that means the conducting wires connected there, will be having their own wiring resistance. Okay, because of these three factors: wiring resistance, the inductor resistance, and the dielectric resistance of the capacitor. These three resistive properties, inherent resistive properties of these components, capacitor, inductor, and the wiring conducting parts. What happens as a result? The voltage is going to drop. Okay, because it is going to consume some amount of energy there. The resistance is going to introduce some loss. Due to this loss, because of the presence of resistance, the signal is said to be a damped oscillation. We are not going to get an undamped output for a tank circuit alone. But along with the tank circuit, amplifier with negative, with positive feedback, if it is used, it is going to act as an undamped signal generator, otherwise a proper form of oscillator, where it has to satisfy the Bartholin's criterion. What does the Bartholin's criterion say? A beta is equal to 1, feedback is positive. It has only two conditions. The open loop gain A beta has to be equal to 1, and the feedback connected to the system, otherwise to the amplifier, again has to be what? Positive feedback. That means the overall phase difference has to be 0 degree or 360 degree. Right? So this is about the tank circuit, its operation. The losses and this damped oscillations is due to the resistive property, otherwise the resistance offered by capacitor, inductor, and the wiring circuits. Here. So this is about the tank circuit. Now we will see few numericals on the based on the tank circuit. We see few numericals based on the tank circuit. Okay, so in the figure they are giving a tank circuit mentioned here, and yes, of course, about the tank circuit. I just forgot to mention its frequency. Its frequency f is equal to 1 by 2 pi under root L C. Okay. Value of inductor, value of capacitance. Only on two factors the value of frequency is going to depend. Okay, so this is the expression for frequency of tank circuit, right? So they have given an example of tank circuit. To calculate the frequency, calculate frequency of oscillation, otherwise just frequency. A tank circuit is given here, otherwise the given circuit. For the given circuit, calculate the (0.01 microfarad (0.01 microfarad) 20 millihenry and 10 millihenry is given. This is the amplifier input. This is amplifier output. So this is acting between the input and output part of the amplifier, where it is taking a portion of the amplifier output and giving to the back to the amplifier input. Okay, so this is a feedback network also. We can say the feedback network also. Clear? So this is the given circuit. So the F is given by the frequencies here itself. F is equal to 1 by 2 pi under root LC. Here 1 by 2 into 3.142 into under root, where L is equal to L1 plus L2 is equal to 30 millihenry. Okay, so 30 into 10 to the power of minus 3 into 0.01. Okay, so this is what is given to calculate the value of frequency. So how we do it? This is 6.284 simply into 2. I have to adjust this term under root. And you have to always balance the 10 to the power value as a even number. Very important thing to perform the proper calculation. The 10 to the power rating has to be adjusted such that it is a even number. Okay, here. So how we can do that? This can be written as 10 to the power of minus 2, isn't it? 10 to the power of minus 2. So this is going to be minus 5, minus 6. 30 into 10 to the power of minus 11, isn't it? 3, 5, 11. Now it is into 30, so we can write it as 6.284 root of 3 into 10 to the power of minus 5 into 30. If it is into 10 it is done, then it is minus 10. I will write something and explain it. So this value can be given as root of 3 into 10 to the power of minus 10, isn't it? Into 10 we are going to do, so this is 10 to the power of 1, this is 10, 10 to the power of 1 means 10 only. To the power of 11 minus 1 means 10 to the power of minus 10 is what we are left with. Minus 10 taking outside the root, it is going to give you 6.284 into root 3 into 10 to the power of minus 5. This can be written as 10 to the power of 5 by 6.284 root of 3. Root of 3. That is 1.732 into 6.284. That is going to give you 10.88. So this can be written as 1 by, we'll do now 1 by 10.88. 0.0919 into 10 to the power of 5. So this can be 9 kilohertz frequency. 9.19 kilohertz is the answer. Here, so how to do this? I have taken an example of a tank circuit having one capacitor and one inductor. If two capacitors are there, you have to take the equivalent value connected in series. If two inductors are there, you have to take the equivalent value of connected in series. So in series, inductor are L1 plus L2. If two capacitors are given, means you will have to take C1 C2 divided by C1 plus C2. That means parallel series combination of the capacitor. Okay, so here what we have done, we have computed the final value of L. We substituted the value because the final value is 10 plus 20, right? So 10 plus 20 is 30 millihenry. Here the value is 30 millihenry. So 1 divided by 2 pi under root LC. 2 into 3.142. 2 into 3.142 under root 30 into 10 to the power of minus 3 into 0.01. That can be written as 10 to the power of 2 into 6 to the power of 10 to the power of minus 6. Now the value is computed as 6.284 under 30 into 10 to the power of 11 by 3 plus 2 5 plus 6 11. 30 into 10, if we perform this, we are going to get minus 10. So root of 3 into minus 10. Okay. So minus 10 taken outside the root, it is simply by 2. That is why I am taking minus 5. When taking out of the root, that's why I told you always select the value of even number. Okay. That is simply divided by 2. So it is minus 5. So 6.284 into 10 into root 3 into 10 to the power of minus 5. Taking in the numerator, it becomes 10 to the power of plus 5. 6.284 into root 3, 10.88. That is 1 divided by 10.88 is 0.0919. Shifting the decimal point into positions, it becomes 9.190 kilohertz. So this is the final answer and a method to solve for the tank circuit. Clear? Now moving to the next numerical. So now we will look into the Hartley oscillator and we will solve the numericals for Hartley oscillator. So this is about the tank circuit. We will solve more numericals on it. The expression is the expression for frequency, otherwise the formula for frequency for the tank circuit is 1 by 2 pi under root LC, and it remains the same for Hartley oscillator. This is the same expression of frequency that we will be using in the Hartley oscillator. Okay, and also for the Colpitt's oscillator, but what differs is the equivalent value of inductor and capacitor. The same formula will be used. So now moving to the Hartley oscillator, start from it. Right from its circuit. First of all, an amplifier is required, so we are using a CE amplifier which we have studied already. Base, ammeter, collector. To the collector, a RFC choke is connected. That means radio frequency choke, RF choke or RFC, radio frequency choke. R2, R1, VCC, output, coupling capacitor C2, two inductors L1 and L2, and one capacitor. And this is the feedback. Okay, so this is what? This is the circuit for a Hartley oscillator. Hartley oscillator. So basically it comprises of 3 units, that is an amplifier, the tank circuit, otherwise this frequency determining circuit. This is also called as what? frequency determining circuit. Okay, also called as frequency determining circuit, because the value of inductor L1 and L2 along with C is going to determine the frequency of this Hartley oscillator. The frequency of signal it is going to produce. It is going to produce. Okay, so this is V0, where it will get the oscillations. Right. So basically, it is comprising of an amplifier where we are using a CE amplifier, a frequency determining circuit, and a feedback. So this is the feedback. Portion of the output is taken, passed into the frequency determining circuit, and sent to the amplifier as a feedback. Clear? So this is the circuit of Hartley oscillator having a CE amplifier, a feedback path, plus a frequency determining circuit. Right? Now moving to the operation. The same concept, continuous charging and discharging process of the, because what this is again the tank circuit itself. So the same concept, capacitor charges, discharges through the inductors. Inductors will be developing a magnetic field. Again, they will collapse. They will charge the capacitor with opposite polarity, so generating a continuous signal. Otherwise, continuously varying the AC signal. Otherwise, the output voltage like this. Here, about the operation, what happens? Continuous charging and discharging process of the inductor and capacitor is going to generate this output. This signal is given back as an feedback to the amplifier circuit. Okay. Here we cannot see any AC input. So in the amplifiers we normally connect a AC input like this, but here there is no AC input. So what happens? What I have told in the basic operation of an amplifier oscillator, that basically noise is picked up. Noise is picked up. See, there are so many resistors, so many conducting wires, and so many other components present here, through which a very small amount of noise can be easily generated. Okay, that noise reaching at the base terminal of the amplifier will be amplified and is available at the collector output C, where that is fed to the capacitor. Capacitor charges a very small amount of voltage. It charges it. Discharges through the inductor. That tank circuit process happens here, creating an output of the tank circuit. That output of the tank circuit is fed back to the base of the CE amplifier. Okay, clear? Now, as this ground is present between the two inductors L1 and L2, there is some thing you have to know about this. Okay, and that is the two inductors are charged with opposite polarity. Otherwise, the voltage across the two inductors will be out of phase by 180 degrees. So the feedback is producing 180 degree phase difference. So this feedback network, otherwise the frequency determining network, okay, this particular part of the circuit is going to introduce 180 degree phase difference. Okay, if L1 is having this signal, L2 is going to have this signal. That means L1 and L2 are out of phase by 180 degree. The voltage across L1 and L2 will be out of phase by 180 degree. Here. So as they are 180 degree out of phase, inverted signal itself is reaching the amplifier input. The 180 degree phase difference, along with the 180 degree phase difference, signal is reaching to the base terminal of the CE amplifier. Okay. As it is CE amplifier, it is going to produce another 180 degree phase difference. Another 180 degree phase difference. As a result, the output will be in phase. So a total of 0 or 3 60 phase difference is opaque. That satisfies the Barkhose's criterion, making the feedback to be positive. Okay, making the feedback to be positive. Initially, the signal produced by the collector itself is inverted. Already initially it has given an inverted value, that is again inverted by the frequency determining circuit by 180 degree. As a result, total 360 otherwise 0 degree phase difference is introduced and such input signal is applied to the base terminal. As a result, what happens? A positive feedback can be maintained, right? A positive feedback is applied to the base terminal of the transistor of CE amplifier, right? So this is a simple working. A phase inverted signal is applied to the frequency determining circuit, where the continuous process of charging and discharging is going to produce an output of the frequency determining circuit with additional 180 degree phase difference. It is going to produce another 180 degree phase difference. As a result, the inverted signal is being inverted once again. That's why the signal reaching to the base is a positive feedback, right? It is a positive feedback. See here, already an inverted signal is there. It keeps on changing for every cycle. Okay. Considering the positive half cycle first, it is going to give the negative half cycle first here. The negative half cycle produces an 180 degree out of phase, so it is going to become a positive half cycle here. So as a result, positive half cycle is reaching the base. Okay. Clear? So it keeps on changing. What is the important point here is that CE amplifier produces 180 degree phase difference and also the frequency determining circuit, otherwise the feedback is this tank circuit is giving another 180 degree phase difference. As a result, the positive feedback is reaching the base terminal of the CE amplifier, and that is what we require for the operation of oscillator. For the operation of oscillator, this is required to satisfy the Barkhose's criterion, such that this particular circuit acts as an oscillator. So here everything is satisfied. The positive feedback is given. Now, gain of this particular circuit is given by L1 by L2. Okay, ratio L1 by L2, and the beta is given by L2 by L1. So as a result, A beta is equal to what? 1. So even this condition for the Barkhose's is satisfied. So this condition of Barkhose's is also satisfied. Clear? So this is about the working of the Hartley oscillator, where its frequency is given by 1 divided by 2 by under root L equivalent C, where L equivalent is equal to L1 plus L2. Where L equivalent is equal to L1 plus L2. Right? So this is about the working, where I am going to repeat the working again. Continuous charging and discharging process is going to create the signal, where the signal with positive feedback is applied to the base terminal. It is going to produce the amplified version of that as an output available at the V. The gain given by L by L2, L1 by L2, beta given by, that means feedback factor given by L2 by L1. So total loop gain is 1. So this satisfies the Barkhose's second criterion, the second condition for Barkhose. Here, frequency is determined by 1 by 2 by under root L equivalent C, where L equivalent is L1 plus L2. So this is about the Barkhose's. Oh, sorry. This is about the Hartley oscillator, right? Advantages. Now we will see the advantages and disadvantages. Suitable for high frequency. High frequency. Oscillators. Suitable for high frequency oscillators. Why? Because always we can just remember it by this expression 2 pi under root LC. See, the capacitor and inductor both will be having the values in the form of 10 to the power of minus values, milli, micro, nano. So as a result, what happens when the value is taken in the numerator? The values becomes 10 to the power of positive values. That's why we can remember from this expression suitable for high frequencies because we are using inductors and capacitors having very high, otherwise having very low values in the form of 10 to the power of minus values, where they move to the numerator to make the value as 10 to the power of plus, making the frequency in the form of 10 to the power of positive values. Right? So suitable for high frequencies. Next. Simple construction. Construction is very simple. Okay. Just by changing the value of inductor and capacitor, the frequency can be changed. Varying frequency is easy. Is easy. So easily frequency can be modified or frequency can be changed. So these are the advantages. Moving to the disadvantages. So what can be the disadvantages? Presence of inductors and capacitors. Capacitors is okay, but due to the presence of inductors, the fabrication of this particular entire unit of Hartley oscillator inside an IC becomes difficult. Not suitable for low frequencies. Okay, as it is suitable for high frequencies, this cannot be used for low frequencies. Okay, so that becomes a disadvantage here. Not useful for low frequencies. Then cannot be fabricated in IC. Cannot be fabricated in IC, and they are having poor stability. And also because of the presence of the inductor, the circuit becomes quite bulky and big in size. Okay, so this is about the advantages and disadvantages. As it is suitable for high frequencies, the applications are also in the high frequency applications where it is used in the radio frequency applications. Okay, it is used in the radio frequency applications. It is used in TV receivers, radio receivers, and okay, where the values of the frequencies you require will be high values. Now we'll take one numerical on Hartley oscillator. Okay. Hartley oscillator frequency is given by 1 by 2 pi under root L equivalency, where L is equivalent is equal to L1 plus L. Okay. So the question given is determine the frequency of oscillations of a Hartley oscillator. Okay, I will just write the given values. Determine the frequency of oscillations of a Hartley oscillator. They are giving 2 bits where N1 is equal to 2 millihenry, N2 is equal to 4 millihenry, and C is equal to 10 nanofarad. Okay, this is the first bit. We'll solve this one and we will move to the second bit. Okay, so frequency is equal to 1 by 2 pi under root L equivalent C, right, where L equivalent is L1 plus L2. So a total of 6 millifarad Henry. We are going to substitute here now. 2 pi under root 6 into 10 to the power of minus 3 into 10 into 10 to the power of minus 9. Okay. 1 by 6.284 root of this makes a total of 12, so I am keeping it as it is. So we will make it as root of 60 into 10 to the power of minus 12. 10, 11, 12, total 12. 9 plus 3, 12. 6 into 10, 60. Right? So we will do the further calculations now. 1 by 6.284 into root 60 into 10 to the power of minus 6. This can be written as 10 to the power of plus 6 into root 6 root 6, that is 2.449 into 6.284. That is going to be 6.284. Okay, 6.284 into 2.449. That is going to give you a total of 1 by 15.389. Okay, so the answer is finally 1 by 15.389 is equal to 0.649 into 10 to the power of plus 6. Okay, so the L equivalent here is 6. Okay, 60 into 10 to the power of minus 12. It goes to the numerator and makes it as, we'll see the calculation once again. Root 2 into 2 pi into root 60. Okay, root 60 into 2 pi we are going to do root 60 into 6.284 is, okay, it is 19.14. Okay, 1 divided by 19.41. It is going to give you the value for root 60. I'll check again into we will check this once again, the substitutions and all. L equivalent 6 millihenry. The given values as 6 millihenry. Okay, 1 divided by 2 into 3.142 into 6 into 10 to the power of minus 3 L equivalent into 10 to the power of minus 9. That is going to give you the value is 6.184 into, we have to make it the power of an even number. 6 into 10 is 60 into 10 to the power of 12. That is going to give you the value as 10 to the power of 6. Coming outside it becomes minus 6. In the numerator it is going to become this. Okay. So here we are going to get the value as 20.54, 6.184 into root 60, 20.54 kilohertz. Okay. Yes. So this is 10 to the power of 6 divided by 284 into root 6 10 to the power of 6 by 48.67. So now I got the correct value, the same thing. So 1 divided by 48.67, 1 divided by 48.67 is 0.205. 0.205 into 10 to the power of 6 is equal to, if we shift the decimal point up to 3 points, 20.5 kilohertz. Okay, that is approximately equal to what we have got. Okay. So this is the answer for bit A. Now we will do for the bit 2. So how we have done here? 2 pi L equivalent. The total L equivalent is 6 millihenry. Okay, 2 into 3.142. 6 we have to balance such that it makes a power of even number. Okay, 10 to the power of minus 12 into 60, 6.184 into root 60. We are taking the minus 12 outside, becomes minus 6. In the numerator becomes plus 6. Okay, 6.284 into root 6 is 48.67. 1 divided by 48.67 is 0.0205 into 10 to the power of 6. Shifting the decimal point by 3 numbers towards the right, it is going to make it as a kilohertz. So 20.5 kilohertz is the final answer for the given values. Next, the next bit we are going to see now. Now the given values are 1 milli, 3 milli Henry, 1 millihenry, 3 millihenry. Total L equivalent is equal to 4 millihenry. C is equal to 0.1. 0.1 microfarad. Okay, 0.1 microfarad. Where frequency F is given by 1 divided by 2 pi under root L C. We have already calculated L equivalent. So 1 divided by 6.284 into under root 4 into 10 to the power of minus 3. 4 into 10 to the power of minus 3 into 0.1 micro. Micro means 10 to the power of minus 6. So how this can be written? Into root 4 into 10 to the power of minus 10. 10 to the power of 3, 10 to the power of minus 1, 10 to the power of minus 6. Minus 4, 6, minus 10. 1 divided by 6.284 into 2. Root 4, 10 into 10 to the power of minus 5. This can be written as 1 by 2 into 6.28 into 10 to the power of 5. So how this can be calculated now? So now the value is 2 into 6.284. That is 1 by 12.568. 1 divided by 12.568 is 0.795, 0.0795. 0.0795 into 10 to the power of 5. So how this can be written? Taking 2 decimal points, because it is 10 to the power of 5, taking 2 there, it is left with 3, that is K. Frequency is equal to 2 decimal points shifted means 7.95 kilohertz. Okay. Frequency is equal to 7.95 kilohertz. Right. So how we have calculated, taking the values, we have taken the equivalent as 4 millihenry. Here the frequency expression is given by 1 divided by 2 pi under root LC. 1 by 2 pi means 6.284 into under root 8 milli 10 to the power of minus 3 minus 1 minus 6, total minus 10. Giving the value as minus 5 outside the root, in the numerator it is going to become plus 5. Okay, divided by 2 into 6.284. Okay, the value is going to be 1 divided by 12.5, 0.0795 into 10 to the power of 5 is the answer, whereby shifting the decimal points we have arrived at the value of frequency, where the value is expressed in the form of kilohertz. Okay, so in the numericals, the calculations part that we have to remember here is to operate the roots. Okay, to operate the roots, you have to be very clear about. Okay, always take it as an even value, so that you can easily bring it out from the root. So simply even value divided by 2, it is going to give you the value outside the root, and taking the value in the numerator is going to be a simple task there, right? So that is one thing, and another thing is always the units. Don't forget the units. Mention in terms of kilohertz, megahertz, standard values. Okay. And also you have to remember the power. Milli means 10 to the power of minus 3, micro means 10 to the power of minus 6. Okay, nano 10 to the power of minus 9, pico minus 12. Okay, kilo 3 plus 3, 10 to the power of plus 3, mega plus 6, giga plus 9. At least these important powers you need to know, right? So we have discussed about the Hartley oscillator, where we have seen the advantages, disadvantages, the operation, the circuit we have seen. We have performed numericals on it. We have also seen the tank circuit, and we have seen one numerical on tank circuit also. The simple expression, almost the entire calculations depend on this expression 1 divided by 2 pi under root ELC. When we are using the 2 inductors, we have to take L equivalent. If we use 2 capacitors, then we have to take C equivalent. That's it. Okay. So we have discussed about the Hartley oscillator. Next class will be dealing with the Colpitts oscillators and further other oscillators. So this is all about today's class, students. Thank you.